Well, we know that sometimes graphs speak louder and better than text. So here, I'm using a graph to illustrate how to understand and describe, interpret marginal effects in linear models. So here we have this equation, right? Y equal to 0.5x plus 4. And without the error term. Of course, if you want to coerce to have error term, the error term can be absorbed into the constant. So really, it doesn't matter. The key here is the coefficient in front of predictor x. Okay, and because the coefficient of the slope is equal to 0.5, we can safely interpret the relationship between x and y as for each unit increase in x, we would expect y to increase by 0.5, 0.5 unit on a scale of y, depending on the substantive scales of x and y. So when we have a concrete empirical problem, we have to use their substantive units, as opposed to using generic units I'm describing here. So here we have x plotted along the x-axis and y here, right? And let's look at, this region of the graph. So this is the line. This is the line summarizing the relationship here, right? A represented relationship here. So here we have delta x that is changing x, which is equal to 2. And we have delta y that is changing y equal to 2. So in this case, we simply change x from x equal to 2 to x equal to 4. What is the amount of change in y? Well, we can carry out the computation. It turns out to be equal to 1. So if we take a ratio of delta y over delta x in this case, well, recall the definition of marginal effects. The definition of marginal effects is the limit of delta x approaching zero, delta y over delta x, the ratio, right? Ratio. So in this case, the ratio is equal to half, which is exactly the coefficient here. A lot of people say, well, let's change the amount of change in x. So let's change x, delta x to be equal to 0.5. So let's say change delta x from, let's say, 6 to 6.5. Then what is the amount of change in y? Well, delta y turns out to be 0.25, if you perform the computation. Again, we take a ratio. The ratio is equal to what? 0.5. So in this case, for a linear regression model, no matter how you manipulate the amount of change in x, the ratio of delta y over delta x is always equal to the coefficient, regardless of the starting point for x and ending point for x. Okay, so that is a very powerful and interesting feature of linear models. That is the coefficient in front of predictor is exactly equal to the marginal effect of that predictor on a response variable. Okay? So no matter how small we shrink delta x, it doesn't matter. Okay? If we carry out the computation, okay, for the starting point of y and starting point of ending point of y, take a difference to get delta y, then take a ratio of delta y over delta x, always going to be equal to, in this case, 0.5, or always going to be equal to what? The coefficient in front of x. Only in linear models.